My name's Dr. Kylie Good. I'm a teaching and research fellow here. I originally trained as a biochemist, then did an engineering doctorate here, which is essentially a vocational PhD, for want of a better word. So you're actually working on a research project, but you actually are working in the industry as part of completing that research project. I'll just give you an overview of the pilot plant. It's essentially a 3-tank system, something like you would find in industry, where you can have water and cleaning chemicals fed into any series of the tanks. It's essentially a system where you can then pump that water or that cleaning chemical around the system through a series of automated valves that are controlled by the PLC. Again, you've got the option of heating that water, so we've got steam fed directly onto a heat exchanger, which again, as you're pumping the water around, you can heat that up, controlled by a steam valve. Some of the other raw materials you could have, so the actual kit is used to look at the cleaning of different kinds of products, so you could put something in there like a toothpaste or a shampoo or even a food product, something like that. And again, pump water or cleaning chemical round and actually monitor the cleaning of that through a series of online measurement probes that we've got, flow, conductivity and turbidity, for example. In something like a CIP system, startup and shutdown are they're very important, because essentially if you've got poor control during those stages, you run the risk of safety issues, especially if you've got people working in that area. So for example, if you were using steam, which we have here in the case of the heat exchanger, and you had the steam valve open too fully, you run the risk of potentially overloading the pipes with too much temperature and pressure. If you haven't got air on to the automated valves before you're trying to run them through the PLC, obviously nothing will happen, but you'll get issues over time, especially with trying to pump with the pump if it's got no power and things like that. The CIP pilot plant control, we've essentially got it set up in MATLAB. Obviously connected to the PLC, and we've got within the panel a series of cards that connect to whatever instrumentation we've got. But on the pilot plant we've got a series of flow meters, conductivity meters, turbidity meters and temperature probes as well. So some of the process control techniques we've got on the pilot plant we can relate to some of the undergraduate modules like process systems and PPC. In terms of the pumping process, in practice you have different kinds of pumps that you could use depending on the viscosity of your material. So in the case of the pilot plant, because we're using water, it's essentially a low viscosity material, so you use something like a centrifugal pump. So some of the pumping processes you'll see in some of the undergraduate modules like momentum transfer and fluid flows. To explain the heating process in a bit more detail, essentially what we've got set up with the pilot plant is live steam coming from the steam main onto a plate heat exchanger. So essentially the water will flow in a counter current direction to the steam and be heated up to whatever set point temperature you control and measure to. CIP, or cleaning in place, is essentially a system that industry use to manage the hygiene of their plant condition. So any of the internal surfaces of the plant will be cleaned normally by this automated CIP process. So essentially, as we've said, we've got a series of tanks with whatever cleaning fluid in them, whether it be water or an alkaline or an acid, something like that. You essentially flow it around your process kit that you've done your production on, so whether that's a food-based material or anything like that, until it's clean to whatever standard you're trying to achieve, whether that's something that you've measured online, like with the conductivity or turbidity, but normally you'll also have that backed up with some kind of microbial swabbing or enumeration technique, and you're making sure that your final surface and your rinse water is clean to a certain microbial standard. The CIP process is fairly standard in how it's designed actually. So you will find it in lots of different industrial types like pharmaceutical, oil and gas potentially, and also in the food industry. It'll be a case of the level of clean you're trying to achieve in those different industrial areas that will dictate how long you clean for and how you actually measure that level. So this sort of field of research and teaching in terms of the CIP process, there could be some interesting future work that we could do, and we've started looking at it now, where you could potentially take different products and characterise certain parameters about that product, like its rheological behaviour or something like that, how it's affected at different shears and temperatures, and actually use that to try and predict how it might clean in a CIP sort of situation. And actually the end game of that could be quite valuable for industry, because you could in theory come up with a sort of cleaning index whereby you put in a few key parameters of your product, a few key parameters of your process, and you'd actually be able to predict how long it would take to clean that product. Some of the results we've had so far from the pilot plant work have been quite useful, both from a general research understanding point of view and also to some of the industrial partners that have been involved. So for example, we've had quite a few different products that we've been able to take and characterise the cleaning of them, and actually in a lot of cases you find that you can reduce the amount of water, the amount of heat required, so you can actually clean at lower temperatures, and sometimes even reduce your flow rates as well.